So, in the first lecture of this module on electric field and magnetic field, I did an experiment. If you remember, we had this glass vessel tray and an aluminium ring which we connected to one terminal of the cell. And we said that this entire aluminium ring is at the same potential as that terminal of the cell, and that always happens. If you have a conductor and if no currents are going in the conductor, all parts of that conductor will be at same potential. Now, if you have two conductors, suppose you have two conductors and connect them to the two terminals of the battery. Suppose you have a conductor, some conductor here, some conductor A, and nearby you also have some other conductor B, and you connect them to a battery or a cell. This is the symbol for battery. The longer line represents higher potential, the smaller line represents lower potential, which we generally take 0, but not necessarily. So, if this is 0 and this is all conductor, this is connecting wire made of conductor, and this is a big conductor here. So, this potential will be same as this potential, 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 this potential. This entire thing will be at one single potential, which you can call 0. So, here you say that V is equal to 0. Similarly, this entire conductor and this connecting wire will be at that same potential as this terminal of the battery, which you can call, say, some V naught or something. So, there is a potential difference between these conductors, and if potential decreases as you go from A to B, the potential decreases. That means you have some kind of electric field in between. So, electric field can be created just by taking two conductors and joining them to the battery, and this kind of combination is known as a capacitor, which is very important element in all kinds of circuits and electronics and things like that. So, you have this capacitor. So, this is known as capacitor, and if the electric field is there, you must have charges which are producing this electric field, and so by connecting it to this cell, you bring some charges on the conductors. On this conductor, let us say we bring plus q charge, and this conductor we bring minus q charge. Everything is neutral, it is only the redistribution of charges. So, if plus q appears here, minus q appears here. Now, there are some terms. First is, let us say, this charge. So, there is a term called charge on the capacitor. As such, the charge on the capacitor is 0. You have plus q charge here, minus q charge here, it is 0. But this term charge on the capacitor is used for the common magnitude of these two charges, plus q and minus q. So, that q, common magnitude, that is known as charge on the capacitor. Then you have this potential difference, this V and this V, potential difference here. So, that is typically known as voltage on the capacitor. V. Here it is V naught, but let us say V. V is the potential difference between these two conductors. So, that is known as voltage on the capacitor. And the ratio, if you take the ratio C, which is this Q divided by V, that is known as capacitance, and this is the quantity which is which is used in all circuit analysis and all that. So capacitance, typically written as C, is this Q divided by this V. So what would be the unit? Q charge is measured in coulombs, SI unit. Potential difference is measured in volts, and when you divide coulombs divided by volts, the quantity you get, the unit you get, is known as farad. So this is measured in farad, written as capital F. Normally the capacitors which are used in various circuits, the capacitance will be in microfarads, few tens of microfarads or 100 microfarad. 1000 microfarad will be called a very big capacitor or large value capacitor, and so on. So let us do some experiments and try to measure some capacitances. The first advantage or a big thing is that measuring charge is very difficult. Measuring charge here is very difficult. But measuring potential difference V is not a big deal. You can use voltmeter, multimeter, whatever. Similarly, for measuring this capacitance also we have instruments, simple instruments known as capacitance meter. Okay. So we will be doing some experiments. We will construct some capacitors and measure its capacitance. So let's do that. First, let me show you the meter. This is the meter, capacitance meter, and we have set all those values, range, etc. And the display which is here is in picofarads. If you can see on this right side, the small letters, it's written PF. So it's picofarad. So pico means 1 by 1000 of a nano, 10 to the power minus 12. So those many farads, right? So it will measure in this. This 0.3 is your zero error, you can assume that. These are the two conductors, steel glasses. There are two steel glasses, and we will be doing our experiments with these. And you can see they are wrapped in some kind of polythene or some non-conducting thing, but then we have made some slot here where I can connect my clips to the metal. So one of the conductor I am connecting to one side of this meter, and the other one I am connecting to other side of meter. This meter itself has batteries, etc., which will apply voltages and measure some current, some circuit is there. It gives me directly the capacitance. So I am just connecting it. Yes, here it is. So the two conductors are placed side by side, and the capacitance is being measured. It's 19.4 picofarads, 19.5, so around 19.4, 19.5 picofarad is the capacitance of this capacitor which is here. If I take them apart, the capacitance has decreased. It has become 16.8. If I bring them close, it is increased 20.7. If I put one inside the other, remember the metals are not touching each other, they should not, otherwise they will be one conductor and one potential. So that cover, that polythene cover is helping me. 37.4 picofarad. Push it further, 61. Push it further, 131.8 picofarads. So more and more area is in front of each other. That's the effective area. In fact, when I am putting it this way, the effective area is very small. The area which is facing each other is very small. When I am pushing it here, the area which is facing each other is quite high. So your capacitance increases if the facing surface area is larger. And of course, the distance is very important, distance between the conductor, average distance in whatever way you measure is important. So, next let us take some more capacitors, make some more capacitors. Let me take these two wires, plastic coated wires. These are two conductors and they are coated with, or cover is this non-conducting material. So, if I connect one of them here, another here, see what happens. Do we have some capacitance? Do we have some capacitance? Yes, this is also a capacitor and the capacitance is 15.8 picofarads. So, that is the capacitance. Commercially, the capacitance which are available in market, they are of different types and different shapes, and accordingly they have different applications. This is known as electrolytic capacitor, and if I can measure its capacitance, let us try. So, I put one clip here and another clip here and is out of range. So, I have to change the range, still out of range. This is nanofarad range I am trying, 20 nanofarad range, no, 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 here it is. Now, on the display that PF has changed to mu F. If you can read that, it is mu F, right here in the right corner. Previously it was PF, now it is mu F. So, microfarad, 996 microfarad is 1 millifarad in fact. This capacitor is 1 millifarad. So, 996 microfarads is a strong capacitor or very large value capacitor. You have other capacitors of different shapes and they have different applications and all that. There are many interesting experiments which can be done with capacitor. So, I will be just showing you one, and for that what I have is a battery, 9-volt battery. This capacitor, this is that same 1000 microfarad capacitor. This is an LED, red color LED. There are two these terminals, one is longer, one is shorter. So, positive must be added to the longer leg and negative to the shorter leg. Then I have two resistors. These are resistances. This is 1 kilo ohm, 1000 ohm resistance, and the other one is also 1000 ohm resistor. So, we have these things and then some connecting wires. So, these are the operators with which we will be doing the experiment. So, look at the connections that we have made. Here is the capacitor, and then from this capacitor I have connected an LED here, it is a red LED, and then a resistance here, 1K resistance, 1000 ohm resistance, then another resistance here, same value, and then the other end is hanging. So, if I touch it here, the circuit will be complete. Of course, there is no power here, no voltage here, so nothing glows. Now, this cell here, I will be connecting it to the capacitor, so that the two conductors or conducting parts in the capacitor will be at these voltages and some charge will go on the capacitor plate. So, now I have touched the battery here. so that now this is at that same voltage as this battery. Now you look at that LED. I am going to complete the circuit by touching these two. Look at the glow and see how the intensity is becoming dimmer, and estimate the time for intensity to become significantly low. Just estimate in your mind. Now my next part will be, instead of these two resistances, I will be using only one resistance. So this time I will connect it here. So the other resistance is out of the circuit. I will just connect it here. Only one resistance will be there. So I am charging the capacitor by touching this terminals of this cell, and now look at the brightness and how much time does it take. See, already it is very faint. It is much faster here. It is quickly it discharges. Once again, this I have charged, and now I am connecting it to the LED, and see how fast the brightness becomes much smaller. So the factor which governs this rate of discharging is the product of capacitance and resistance, C into R. The capacitance multiplied by resistance. If you take this in farad and this in ohm, this product will be in seconds. It has dimensions of time. So this product will decide how much time it is going to discharge significantly. So in our case, this capacitance was fixed, 1000 microfarad. But in one case we had a lower resistance, we used only one resistance. In the other case we used two resistances, so this was doubled. So this is called time constant. So that time constant was doubled, and therefore it took more time to discharge. So now let me move on to magnetic field. When we talked about forces between two charged particles, we said that the force is mediated by electric field produced by these particles. In the same spirit, any magnetic force is mediated by another kind of field which we call magnetic field. So if you have two magnets attracting each other, or a magnet which attracts a pin, iron pin, or if you have currents which attract each other or repel each other, these are all examples of magnetic forces, and again a magnetic field is created and that field exerts force. So how the field is created, what is the source of this field? Electric field is created by charged particles. How is magnetic field created? Magnetic field is also created by charged particles, but then moving charged particles. If the charged particle is at rest, it will not produce magnetic field, but if the charged particle is moving, then it will produce magnetic field. Current is nothing but flow of charges. Therefore, if there is a current in a wire, it will produce magnetic field. We also have magnets which produce magnetic field. In magnets also you have tiny atomic currents, and it's this current which produces magnetic field. So we will be studying how the fields are created, and in turn what this magnetic field does to the charged particles. If you have a charged particle which is at rest in the magnetic field, magnetic field does nothing to it. It does not exert any force. But in the magnetic field, if you have a moving charge particle, then yes, the force will be there. Similarly, if you have current in a magnetic field, yes, then the magnetic field will exert force on the current.